The first part of the Fundamental Theorem of Calculus tells me that if I have a continuous function little f, there's always a way to produce an antiderivative of f by using the cumulative area idea. The second part of the Fundamental Theorem of Calculus says that if I have a continuous function and any antiderivative, whether it be the one I produce in that fashion or a different one, then I can use that antiderivative to evaluate the definite integral. That the definite integral from a to b of little f of x dx is big F of b minus big F of a. Finally, the two parts of the Fundamental Theorem of Calculus connect antidifferentiation with the areas we've been studying. So, I'd like to prove the Fundamental Theorem of Calculus Part 2 in this video, and then do a lot of examples using the Fundamental Theorem of Calculus Part 2 to evaluate definite integrals. We start by letting big G of x be that particular antiderivative I can form through the ideas of the first fundamental theorem of calculus. Because I automatically know that this function has derivative little f. This function big G is an antiderivative for little f. I need to show you that this statement is true for any antiderivative. The second corollary to the mean value theorem says if I have another antiderivative for little f, it differs from big G by at most a constant. That any other antiderivative is this one plus some arbitrary constant c. So now I have my any antiderivative, right? It's just this function plus c. So I want to investigate now this arithmetic and show you that it really is equal to this definite integral. So f of b minus f of a, because of this equality, would be g of b plus some value c minus, and now f of a would be, well, g of a plus that same arbitrary constant c. Right away I see the arbitrary constants cancel out and that f of b minus f of a is g of b minus g of a. Well, now what I want to do is think about what g of b is. Well, if b goes in for x, then b goes in for x. And what g of a is. Plug a in, plug a in. So g of b minus g of a is the definite integral from a to b of f of t dt minus the integral from, well, a to a of f of t dt. The zero width property says this part is 0. This is the definite integral from a to b of f of something d the same something. And this is an important part, right? Remember the t was a dummy variable. As long as this is a t and that's a t, this is the same thing as if that was an x and this was an x. Or a Batman symbol. Or whatever you wanted it to be. So, we have proven the Fundamental Theorem of Calculus Part 2. This definite integral is equal to f of b minus f of a. Now, we do this calculation so often that you'll see a shorthand notation that if I have an antiderivative, I'll write it down and then say, well, I'm going to evaluate it from a to b. So when I write something that looks like this down, it means I'm going to plug b in and then take away what happens when I plug a in. And it would be okay to use the brackets on both sides if it was in a more complicated expression. But it's simply telling us the order to do the subtraction. Plug in b, take away what happens when I plug in a. Our next video is going to have plenty of examples of using the Fundamental Theorem of Calculus Part 2.